All right, so you want to start with number 4?
Yeah, number 4.
So is this enough? Yeah. So it's like a beam with two. I think I read it before. I forgot it. It's a beam with two things holding it up, right?
Yeah, two wires, two cables.
So it's like this beam, and then there's like one here, the ceiling, whatever. And then one, say here. Because they're not the same distance from the end.
Right.
So, as usual, I'm not going to do any of the numbers.
Yeah, no.
That's boring. But, so I'll say like D1, D2, and it has a total length, maybe L. So, of course, if we wanted to find the distance in the middle, we could subtract, but. And then has some mass. And then it tells us about the diameter of the wires, but we'll deal with that later.
Mm-hmm.
Okay, so it seems like this has two like parts, right? Like the first, so first it's like a torque statics problem, right? As you said.
Yeah.
And then once we have the tension, so basically we want to find the tensions on these two wires, right? Once we have T1 and T2, then we can use the whole other thing with the, it's made of steel and there's an elastic limit or whatever, and all that stuff. So that's all like a separate thing. That literally all the what do you call it, Young's modulus and all that stuff relates to the forces, the tensions on a wire.
Yep.
So basically it's like two separate problems, right? Okay, so for the tension, well, we know that the sum of the force. So first I would just say, well, the easiest one is to do the sum of the forces, right?
Mm-hmm.
For statics, generally, you can just say sum of the forces is always going to be 0, of course. So, well, the only forces on here are gravity, right, mg, and that must be equal to. So I'm sort of skipping a step. Obviously, I would be subtracting the upward ones and just moving them over to 0.
Mm-hmm.
So, or you could just balance them. Mg is equal to T1 plus T2, right?
Right.
So that's pretty easy. But and so that means we only actually need to do one other equation because there's only two unknowns here, so we only need one other equation. So well, we could do right. Okay.
2 moments.
Yes, we could do the torque, the sum of the torques. So I'll just say this is the sum of the forces is 0. Gives this. Now we should do the sum of the torques is, of course, going to be 0 around any point. Well, we have to pick a point. Well, you might want to pick one of these points, which we can do. We could pick, we could pick one of these points because then the torque due to one of them is going to go away. So we don't have to worry about it. The problem is that if we, I guess it's not a problem. I was thinking the moment of inertia would be kind of hard to compute, but we don't even need it because it's 0. the acceleration is 0. So, let's do this point here. So the sum of the torques, well, there's 2 torques around this point, right? There's the gravity, and then there's an upward one from the other thing, right?
Mm-hmm.
So the gravity is going to be, well, the force is mg, so this is force times distance, which is going to be the distance from here to the center of mass. Well, if it's a rod with a length L, the center of mass is at L over 2. So this distance here is L over 2.
Oh, that, okay. I thought you meant T1. I thought you meant T1. Okay.
No,
I
yeah.
was like,
well, we do need this D1 here because
Right.
it's going to be L over 2 minus D1, right? That's the distance.
Yep.
That's the distance between here. Right, it's that we want the distance from the place where we're taking the torque to the center of mass, which is where the gravity is located. The force of gravity is, applied. Oops. Yeah. Okay. Okay, so this is torque 1. And, okay, we'll leave it like this. But the other one's going the opposite direction, so we just need, it doesn't matter which is which, we just need a minus sign at some point.
Okay.
Or we could do the same thing we did with the forces, which is just say they have to be equal. It has to balance out. That's of
Mhm.
course the same as saying that the difference is 0.
Mhm.
You know, so now this one's going to be t1 or sorry t2 times that's the force times the distance, which is going to be it's going to be L minus d1 minus d2, I guess, right? Because
Total length minus.
it's going to be, we want this distance here to here.
Okay.
So it's just going to be L minus d1 minus d2.
Oh, the distance between the two torques.
Distance between the point we're measuring, the point around which we're measuring the torque to where the torque is applied.
Oh, okay.
Because this, really, we shouldn't think of this as a torque. This is
Yeah.
There's no torque associated with that force. But anyway, so yeah. We could have done it the other way, of course, and we just get another different equation. But luckily, everything here we know they're given except for T2 and T1. And we have 2 equations with them in them. So, of course, we could just solve for T2 and plug it in, and we could get an equation. Right, if we solve for T2 here, and we plug it in here, we get an equation with just T1. Solve for T1, then we can plug back in here and get T2. Of course, we could also consider the torque around, like, the middle. Like, we consider the torque around the center, and then gravity would contribute nothing, but we just have a torque this way and a torque this way from these two, and so we get something that looks like this from the other one too. Anyway, of course, or you could do from the other point, you could do from the end. If you do it from the end point, of course, it would have 3 torques. All these, there's various levels of how complicated it's going to be, but of course, they have to give you the same answer.
Depends on what point you pick.
Right, because it's equivalent to say that it's not rotating around this point.
Yep.
As any point, right? So, yeah.
Straightforward.
Yep, and then you plug these in. Okay, so then you solve this as an algebra thing. But let's say we have T1 and T2, and then they want you to use the Young's modulus or something like that.
Yeah. Would you, using the values in problem 3 for elastic constraints of steel, would either wire have exceeded its linear elastic limit? How long would each wire be if the beam were removed?
Yeah.
Do they give you a length? Oh. 2 meter long steel wires. Okay.
Okay.
So it's obviously because of the weight it's stretching them. So
right.
It wants to know what their original length is before. Okay.
So what's I don't remember any of the formulas for it's like
yeah, we got 'em.
Sigma is epsilon E or something, and this is the pressure. Well, they don't call it. They call it something else, but it's pressure. Stress. That's right. So this is the stress, and this is the strain, I guess.
Strain times the elastic modulus. Yes.
Yeah. So the strain is like L naught over delta L over L or something.
The change in L per original length. Yeah. So
So it's like a
per inch.
1.1 or something. Why do none of these really show up? Okay, so and then this stress has units of it's a pressure. They don't call it. It's a one-dimensional pressure. So it has units of force per area, and so for the force, the force here is going to be, so if they want you to somehow what would they want you to compute? Right, they want you to compute the strain, I guess, right?
You'd get the
Right, so we could do sigma over E, or if you look up E, you supposedly can look it up, I guess.
Yeah, they provide it.
Yeah, good. Okay,
Yeah.
and then sigma would be the force, which is the tension, divided by the cross-sectional area. And of course, if they give you the radius, you could do pi r squared, right? And then all over E, which is a number, and then you could get some number, and it's probably going to be 1.2 maybe. I'm just making it up, but it's going to be something like this, which means it gets 20% longer, right?
Yep.
The delta L over L would be 1.2, means that the new length over the old length would be... Actually, I don't know if that's what it looks like.
If
Actually,
it
sorry.
20% would just be 0.2.
I think it would be, you're right. So 0.2,
Okay.
So 0.2 would be, yes, you're right.
Okay.
I don't really do the problem, so.
I just
So
understand.
something like this, and then, therefore this becomes 20% longer. If you have a strain of 1, that would mean gets you twice as long or something.
I'll be right back.
Sure.
So you did 2.
There's our marker.
So we're over. What diameter cables would you recommend? Okay, so yeah, then factor of safety.
Yeah, then you have to like plug in some safety things. Sorry.
Oh, baby. Shoot.
Right, if you use like a 3 times.
Yeah, 3 is usually typical. What? Seems pretty straightforward.
Right, so you want. I guess what they mean. I mean, you probably know better than me. The safety margin of 3 means that.
You take whatever that minimum is, because that would basically be your minimum,
Yes,
and then you
triple
multiply
it,
by 3.
and then you're gonna solve for R.
Yep.
Okay,
So
I see.
your R-
Yeah, all right, sure.
Whatever R makes your value triple.
Which would be like, well, I don't know, I can't do it in my head. Anyway, something.
I don't know.
Okay, that makes sense.
I think I'm good with the other 3. They're pretty straightforward,
Yeah, this
and then just reading. That's no problem.
the confusing thing was when he was talking in class, I think, about it. He was giving an example that was, I think, very specific with the knife. I remember,
Yeah,
was it Sean or someone was asking.
Dio
about
was asking about that.
it. Okay.
He lost me, but I understand like how it worked.
Yeah,
But he lost me when he was talking. I was like, he's going too deep. I kind of.
something about the knife and 3-dimensional. I didn't quite even know what he was talking about.
It was like the more. I think it was the greater the cross sectional area, the harder it was to cut it. Something like that.
Yeah, well, it should make sense. Just if you have a sharp knife,
more
it's
material
easier.
under it.
Yeah,
That's what
exactly,
I'm thinking.
exactly.
Cutting farther distance to go.
I thought that's what he was saying, and then he said something. I don't know. His point was probably very subtle,
Yeah.
but I didn't quite get it. But reading through the chapter, it actually seemed a little, there's a bunch of these equations. There's this, and then there's one for like if the force is tangential, and then there's another one for if it's like 3-dimensional, like a bulk modulus.
Okay.
So, but they all have this form.
Yeah, he lost me on rotational matrices. It was just rotating.
Yeah.
Maybe
I would love to talk
just
about
to
it.
see what he needs.
That's my favorite. That's much more fun than this.
I was gonna say it must be for you. Yeah.
I mean, these problems I'm sure get fun, but this is a very they want you to learn this relationship or whatever, which
Yeah.
is not even a relationship; it's just a definition
Mhm.
of E, and it's a definition of everything basically. So it's a little bit silly because they're just getting used to using a new thing,
Mhm.
whereas the rotation matrices are like a really powerful tool.
I'd like to hear what you have to say about that, Alex.
Yeah.
The other night, Christos lost me on rotational matrices.
I remember. So what would you like me to hear about?
Well,
gonna
so
go over it.
so far we just did number
We just
4.
said number 4.
Which was just it was like a beam hanging from 2 things, and it's like a torque and force
All right.
equilibrium problem.
Let's see. That was 4.1, right? Sorry. Chapter 3, problem 4, or problem.
Chapter 5.
5, problem 4.
5.
Um,
I'm sorry, I'm late today. So
No,
I wrote that.
you're not. No one's late. I do whatever. I just didn't want you to miss it.
No, I appreciate it. Thank you. Okay. So,
It's a static
using
problem.
problems of 3. Oh, that's actually good.
yeah,
Nice.
it's a statics problem.
Dynamics
Yeah.
is a pain.
Yes.
All right. So problems of 3. All right. With wire exceeded. All right. Solve problems 2 and 3 at the end.
Yeah, they're wicked straightforward.
All right. Solve problems 1 and 4 at the end of chapter 5. Okay.
One's just definition, really, just give an
Okay.
explanation for something.
All right. That's straightforward.
And 4 is like the math one.
All right. And
Yeah.
what about problems 2 and 3 at the end of chapter 3? Have
Yeah,
you
we can
those
talk about.
Houghton wants to get it. I'll be back.
Oh, sure.
Don't wait for me.
2 and 3 were like I think something with a ramp, and they asked which time something falls faster
Chapter 4.
or gets to the end of the ramp first.
Yeah.
Yeah, we can talk about that real quick.
Chapter 4, problem 1 and. Sorry, chapter 3, problem 2.
Yeah, no, they bounce around.
Give me a wallet. Be nice to have.
Okay, well, we're not thieves here. Oh,
No, I need to get back in. My card.
Alright. No, then we ask you for money.
Right, exactly. Is it okay if I erase this?
Yeah, let me just check something. So,
Yeah.
Using the values of problem 3, would either wire have exceeded its linear elastic limit? Alright, and we can figure out linear elastic limit from using Young's module, or sorry,
Yes, the limit would be the. Actually, I don't know. I mean, it's all somewhere here. I don't know exactly what they mean by the. I mean, by the limit, they would mean like this
Yeah.
thing, which is the strain. Like there's a certain.
So when the change in length is greater than the total length allowed, then that means it overdoes it?
I don't know if that's. I don't know if that's exactly right,
Okay.
but there's some limit to the change in length, I guess.
Okay. And when it says how long would it have to be, that's 0.2, right?
Yeah, I just made this up. This is not the real answer. I was just giving an example. I didn't do any of the numbers, but I was just showing that it's first of all it's a force problem, force and torque problem. So that's the whole step 1. Step 2 is once you have the torques, or sorry, the tensions, then it's just a
Okay, so from
stress
using-
strain problem.
Okay, so from using those two definitions over there, we're able to figure out the relationship between T1 and T2.
Yes.
Uh,
To the other
two
ones.
equations, 2 unknowns.
Exactly.
From there, we go ahead and we say, okay, we know we have we have T1 and T2.
Mhm.
We know what their values are in terms of length and distance,
Yes.
right? And so from there, you can just plug it in.
Right. You could plug in, here into the stress that has the force in it,
Mhm.
and there's also the radius of the wire in here
Hello.
too.
Alright.
And by plugging everything in, you can figure out the whatever you want, basically.
Okay.
So
Going from there, just gonna.
yes, it's all on video too. If you
I really like your videos,
yes.
but
The videos are helpful, especially because like when you have it through Monday and Wednesday, I can't come because
Yeah.
I work in Andover and it's like
Oh,
shit.
I
So,
understand.
but
You get here when you get here, right?
exactly. But part of the problem is, and this isn't something that can help. It's
We'll
good. It's good listening to go over everything.
Yeah.
But part of it is because the angle is bad and because that's a very reflective material.
Yes, I did notice that.
Yeah.
Even when I'm seeing it, there's like these two.
Oh, they killed
I was trying to find an angle, but I couldn't. I could put it over there, but then you can't really see. So yeah, I know what you mean.
It's all right.
I'll see if I could maybe put like a paper over those or something at
We
some
should-
point.
We should probably consider like getting you like your own proper studio, like boom.
They
mics and
really
everything.
should.
Yeah.
Yes.
Put aside some money
And
for that.
hire who can play me. Someone can play me. Tom Hardy can play
Thank you.
If you say
Um,
Rowan Atkinson.
Rowan
then,
Atkinson can play you. Yes.
That's kicking while I was down. Biked over here and everything.
That is good. Okay, well I'm gonna erase this, but this is
Yeah.
I just want to say this problem
No, it's all good.
was it was kind of like the second half was actually was the quote unquote hard part because that was the new thing. The first half is something that we've done last chapter, like it wasn't anything super new. So it actually wasn't super like a bad problem. It was just had several steps, I guess.
And so when it says what diameter of cables would you have to use, that was
Yeah.
just those were the values for D1 and D2, not distance.
No, those were the distance from the
Okay,
ends
so-
because they were slightly different, but the diameters would be the
Oh, the pi r
double-
squared.
yes, that would be the
Okay,
radius, and
right,
you have to
right,
double
right.
it, yeah.
Okay.
Because this stress
Mhm.
is force, which is like going to be the tension on the wire or whatever, divided by the area, cross-sectional area.
Right.
So this A would have pi r squared for a circular wire.
Alright. Be an interesting thing if we could use that formula to figure out daily stress too.
Yeah.
We could quantify that.
You
sort
could
of
increase your cross-sectional area.
thing. Right.
You could reduce your stress.
Well, that's what people eat
Perhaps.
so much
Yeah,
food.
that's exactly.
Keegan, I don't suppose you know when the quizzes might be done being
I do not. I'm not grading them now.
Ah.
Oh.
He's grading them, yeah. So
Oh,
who knows?
Damn.
Okay.
All right.
He grades the quiz and the final and all that stuff.
So what? So what have I missed so far? In what terms
Oh,
of
yeah,
because you
just
started
today?
at 1, yeah, today.
We just did one problem basically. The last problem in chapter 5
Oh, number 4. Okay.
Yeah, which was kind of I would say the hardest problem on this homework.
Okay.
Which it wasn't. I'll just summarize it real quick. You can watch the video if you want the whole thing, but it was basically just a statics problem where there's a beam hanging and we solved for all the tensions. There's 2 beams, so we have 2 tensions to solve for. And then once we solved for both tensions, that was like step 1 is done, and we just move on to just use the tensions and a wire, and we can solve for the stress and strain and Young's modulus and all that stuff.
Okay.
So it was sort of like 2 relatively one problem that we've done before, like
Like the,
statics problems.
Yeah, like that's that strange problem with the rod and the ropes.
Yes, that was
That was weird, but it was the
Ridiculous.
same vein of questioning. Right?
exactly. It was like a statics. Everything's not moving, so we can.
Yeah, that was very tricky.
That was
that was an incredible pain in my ass.
yeah.
Yeah, you remember the one about the? Yeah, you remember.
Oh yeah.
Yeah.
Oh.
The donuts.
Yes.
Anyway,
So,
Okay.
and you wanted to. We're gonna talk about rotation matrices.
I was gonna ask you about that. But
Yeah,
Did you
what
want to go
did
over the
you-
solid hollow sphere thing on the wrap?
Oh yeah, we can talk about
Alright.
the sphere
So,
thing.
Go ahead.
all right. If we're comfortable with this,
Yeah.
I prefer to go over the homework.
Yeah. Okay.
Yeah, that's.
Yeah.
2 and 3. Yeah.
Wait,
Yeah.
you mean the one that's due?
Yes.
Yeah.
Preferably.
Yeah. So good.
Oh, I have that sheet. Where'd you go?
Oh yeah, you're talking about from when we were studying for the quiz. That question.
No. Rotational matrices is part of. We're supposed to read part of it, but he
We're- Yeah,
Oh,
rotation
right,
matrices is in the book.
I
presented it
haven't,
in class, and he lost me on it.
Yeah. No. That I think I know about that one, but yeah. Can we do the homework and then we'll go over the
Absolutely.
rotation?
Sure.
Absolutely.
So these actually.
That reminds me. Never mind.
These are still okay. These problems are very similar. I don't know why they shouldn't really be 2 separate problems, but it's basically all these things where we take an object, a round thing. I'm just gonna call it a round thing, and we roll it down a ramp, and then we want to find what do we want to find?
Which hits the bottom first?
Which will reach the bottom first? Yeah. So. Well,
It's the 19.
yeah. So I would say one thing if we just say it starts at a height h, okay, and there's an angle theta, it doesn't whatever, doesn't matter. Now we can talk about the forces and break down the forces of gravity and friction and torque around the thing. That's all fine, but it's going to work, but it's way harder. We could just use energy for all this, right? Because I guess here. Well, I was going to say something. Okay, I'm going to say something really about friction, but it's might be more confusing. But so if you're not confused by this, then don't worry about it.
Okay.
Which is that this is the reason things roll is because there's friction here. Otherwise, it would just slide, right? So you have to have some minimum amount of friction to make it roll. If we're doing an energy problem, how come we don't need to consider this in terms of like if we want to use potential energy to kinetic energy or something? Why don't we need to consider the work done by friction?
On a sphere, as opposed to a
Yes.
cylinder. Oh,
Or on anything?
so
Yeah.
Sorry, because my guess would be because the force of friction is only instantaneous. So like the points at that, so when it's rolling down, the potential energy, the kinetic energy, that's constantly invoked at that point.
Uh-huh.
But the force of friction is both so small that you can neglect it, and at the same time it's only momentary, because there's static friction and then there's dynamic friction, right?
Yes. In this case, yeah. So yeah.
Close enough.
Yeah. I would say yeah, but let me just
Yeah,
say it.
go ahead.
It's so there's no kinetic friction, right? But that's specifically because nothing is actually sliding, right? Things only have kinetic friction if they're sliding against each other, right?
Mhm.
This only has static friction at this single point, and what that means is that when something's rolling, it's actually not like the bottom of it is stopped compared to the block, compared to the ramp. I mean, So the bottom, like when you're driving, the bottom of your tire is not moving compared to the road. So therefore, you can use work. It would just be force times distance, but the distance is actually going to be 0 because each point is not moving relative. Like the force is not making a point move. It's actually making it not move. Does that make sense?
Could you repeat it one more time in 30
So-
words or less?
So, how many words?
30?
Okay. The place the force of friction is acting is not moving in response to that force. Therefore, D is 0.
Force of friction is not moving at that point.
The force is not making the point move. Work is when a force makes something move
Okay.
in response to that force,
Okay.
right? In the same direction, backwards or forwards. So gravity makes things move down.
Mm.
This friction, nothing's actually moving. The part that friction is being applied at is actually always stopped. It's a different point every instant. So yeah, you're right in to say it's like instantaneous.
Okay. So
yeah,
so for our definition of work, friction is neglected.
friction is still there, but the work done by friction is 0. Because the work done by
The
friction,
distance is essentially 0 because it's a different point every time.
Yes. Yeah.
Okay.
That's a way to say it. Yeah, you kind of said what you said was
Yeah, I was
essentially
getting
right too.
I was getting there, but I couldn't quite. I couldn't quite. Yeah, I see what you mean.
The point is, I mean, so this is a very complex way to say that don't worry about it,
Okay.
because that just means we can treat this as a normal energy problem
Okay.
without worrying about friction. So that's why, if it was sliding, we would indeed have to consider friction because the friction is actually making the point move.
Okay, so
yeah.
because it's rolling now, friction isn't actually working on it because
Yes, exactly. Friction is an active, non-zero force. It has to be some significant value. It's not negligible. The force of friction is not negligible, but the work done by friction is not negligible either. It's 0. It's exactly 0.
so
Yeah.
for velocity and acceleration, if you change, even if it's the same value, if you
Yeah.
change the direction, it's not the same velocity. The same thing applies
Uh-huh.
to friction in this case. If you change the direction, it's not the same force of friction. But in response to that, we have angular momentum and angular velocity, right? Where, okay, if you change direction,
Yeah.
then it's still the same. It's still the same angular velocity or angular momentum. You know what I'm talking about?
Not quite.
Okay, so if
Well,
it's
are you saying? Because I would just say, like with circular motion, just a block moving in a circle around a thing. This also does no work, but that's only because the velocity, the direction it's actually moving, is always perpendicular to the force.
I might not be articulating my question correctly. Let's answer the problem and then I'll if we
Okay,
have time,
sure.
I'll- Yeah, but thank you.
So anyway, that's all a very subtle thing.
Okay.
So the point is that this problem is actually relatively simple if you've done the other block sliding out of thing problem, or, sliding out of ramp problems. So we can say the total energy, so it's just energy conservation, right? The total energy before is, well, if it just has a mass m, we can just say mgh, right? That's the only energy before. And the total energy after is going to be, well, it's not going to be, there's no potential energy at the end. There is going to be it's going to be moving at some velocity v, right? So that's going to be there. The center of mass is moving. But it's also, it's going to be sliding, not sliding. It's going to be moving with a velocity, but it's also going to be rotating, right? We can decouple those. There's a physics word, but we can
The total energy is both translational and rotational.
exactly you can treat them as separately. Like you can treat it as
Forces.
I'm using this energy to both move it and spin it separately, and of course rolling is just the same. Those happening at the same time. So then we have to say 1/2 I omega squared, right?
Okay.
But of course, this has way too many variables. Assuming we know h and we know m, v we still don't know, and I and omega we don't know. But of course, the problems, I think it's like 2 and 3, all are just about plugging in I, different values. So for a sphere, we might plug in, was it 3/5 maybe? mr squared, I don't really remember. A hollow sphere is like, okay. There's a math distinction I want to avoid talking about, but which is that, okay. I'll say it. A sphere is actually a two-dimensional surface. A ball is a three-dimensional. Anyway, it's a whole.
Oh yeah,
So
you are technically right. Doesn't that get isn't that topology?
Yes,
Isn't that
yes,
branch
it
in
is
that?
topology indeed. Very good. You should take topology if you get a chance. It's a math class. It's really fun.
I did the math minor, and I basically focused on like real applied stuff and like calc, the different calcs and stats.
Yeah.
But like math majors, I think you had to take topology,
Oh, you did.
and it was.
Yes.
My boy here's a physicist.
So, so we have So a sphere, they'll call it a sphere, and they'll call it a hollow sphere. Spheres are all hollow spheres. A ball is the sphere is a boundary of a free ball, a two-sphere. Anyway,
Is that your fun fact at parties? Hey, did you
Yes,
know
it
this?
is. It's a lot of fun.
Keegan, you're ruining balls for me. Stop.
So, all right. And then what else? A hoop is like mr squared. I'm not gonna write. You have a. You
Yeah,
have
we
it
got this.
Actually, if you look it up on Wikipedia, they'll give you a giant.
Does anyone still have that packet? I left mine at work for some reason.
I think I
just
have
don't know
it.
where it is right now.
There we go.
It's hanging around.
It's in the ether somewhere.
Here we go.
Wonderful.
And then you have like a disc or a cylinder, which is the same as a disc. Same moment, I mean. So whatever, we can plug it in. And of course, once we plug in and we don't have any I, there's no more unknowns. We just have R, which is supposedly known, and M is known. Now, omega is the part where we still have two unknowns, which is V and omega. But of course, and actually that's when I was saying, like, imagine we just take an object and we move it, we sort of translate it at some velocity V. That's not a good way to say it. We accelerate it to some velocity V. We use some energy to make it move at a velocity V, and we spin it. Now this is still right, but of course, if I say it like that, they don't have to be connected at all. The moving, if you just move something and spin it while you're moving it, this is totally right. But of course, when something's rolling, we actually have a relationship between V and omega. So you have to be very careful. You can't always assume that, I think it's very, okay, let me just say so R omega is V, right? This is not always true. I think people get it, I guess people don't really get it confused, but it's very easy to just be like, this is always true for that's omega means V over R. But that's specifically talking about an object that has its center of mass velocity equal to its rolling, basically, so that the bottom is stopped at all points.
Mm-hmm.
And that's another way of saying that is that an object whose angular velocity is omega, the edge has a tangential velocity of V.
So in what circumstance, in what situation, would R omega equals V not be true?
Like, for example, they told you a disk was rotating,
Yeah.
and they have a point halfway on the disk, and they say, what's the speed of this object? It would not be. If you knew omega and you knew the whole radius,
I see.
it of course would be just this radius.
In that case, then
You just have to be careful with that.
okay. So as long as you're consistent with it, right? So
Yeah, I mean, this is true if you just use the correct, then
as
you.
long as you have the correct, as long as you have the correct radius.
Yeah, exactly. Yeah.
And as long as they specify that that's the velocity at that particular point on the disk or the sphere.
Yeah.
Okay, that's fair.
So things moving, an object just moving in a circle, just in like a free body type way, like on its own. This is true, but if you have a big object, all the points on it are moving at different speeds, right? So you have to be careful. The edge is moving at V, and and the center is moving at 0, right? And then depending on how far you are, of course, you could just change this to be just the distance from the center, basically. So it's true, but just because I feel like, well, I guess I don't see anyone doing this, but like in the undergrad classes, a lot of them just say, anytime they're given an object with a radius, they just, and omega, they just plug this in and do things. They just say, well, R is R.
Yeah.
But R can mean the distance from the center, depending on what you're talking about. Anyway, so this was, wanted to clarify that. But anyways, then we could but this is also rolling without slipping because of the same argument, the fact that if we have a thing moving, we actually want the bottom to be stopped, right? Compared to the road. And so if the bottom is stopped, that means that we could also consider it as the bottom has velocity V going backwards, right? This is the same as the bottom being stopped and the center going at velocity V. And this has omega, and this where this is stopped also has omega. and plus the velocity v. Does that make sense? This might be a little more confusing. It might have already been clear why that's true.
Right.
I just think of it like something's rolling without slipping means that the bottom of it is stopped all the time, and the center of it is moving at a velocity v. That's equivalent to saying that relative to the center, each point is moving at velocity v. Oops. Right?
Okay.
So each point at the edge moving at velocity v with a radius r literally means this. So anyway,
Oh, okay.
So
that's just a silly, whatever. If this already made sense to you, then remember what you already thought.
Well, there goes my quiz.
And so then we can plug in, of course, a v over r squared here. And probably the r is going to cancel, and we just get some other thing, and then, yeah. So, of course, the difference between all the problems is just going to be this I. And then, oh, sorry, I should say the answer is, of course, going to be that everything's going to be in terms of v, and so we can solve for v, and it's going to be some complicated thing, but if we get v equals a higher number, in some cases we'll get v as actual higher number. Actually, specifically, it'll be when this number is very low, right? Or sorry. Yeah, when this I is very low, because that just means that less of the energy is going toward spinning it. Right? If you're spending a lot of, basically, it's kind of like you have this much energy, and you're spending some of it on rotating it, and you're spending some of it on moving forward. Now, if you're spending a lot on rotating, you're not going to have much left to move forward, right? But they're sort of locked together because it has to roll, right? So, of course, you can't just separately exchange them. So you have to basically, this is like a requirement, you have to spend this much on the spinning. And so if it doesn't cost a lot to spin, like a disk costs m 1/2 mr squared, this is pretty low compared to a hollow cylinder,
Yeah.
because then you have to make all your mass. Another way to think of it is that a hollow cylinder, to roll it, you have to make all the mass go pretty fast.
Mhm.
Whereas a filled-in cylinder, some of the mass doesn't have to go that fast. It's near the middle. Right.
So it's like a flywheel on a bicycle.
Yeah.
Kind of like those solid discs in the middle.
Yeah.
So we all know how to use.
Yeah, I
flywheel.
remember that. Yeah.
But
I've seen that.
they could make it better. They probably make it for structural reasons, not for physics reasons.
Oh,
But
actually, since we're talking about 3.2, I do have
Yeah.
a question with that. So it says, what about instead of 2 spheres, C, problem 1? I guess
Yeah.
this is just a wording question. Do they want us to do A, B, and C for this case? Is that what that means?
was A, B, and C?
Like it says, consider if we've got 2 solid spheres. Do this if they have same diameter, different masses, same mass with different diameters, different mass, different. Is
No,
just do A, B, and C? But
I think they just mean.
If we do that, then we're considering 2 different factors: different shapes and different masses, different diameters and different masses. And oh yeah, that could work actually.
You don't have to do that. I mean, you can if you want. I think they just mean like
should I
they
interpret
don't
it as
want to.
same mass and same diameter then?
Yes,
I guess.
yeah.
Okay.
I think they just mean they don't want you to think of. They don't want to rewrite rolled down ramp.
Okay.
They just want you to be like, if you did problem 1, just do the same thing, but with these. Yeah, just assume they're the same mass.
All right. So
It should be a short.
But I'm saying like
You
I don't
don't
have to do the different cases like.
No, you don't.
Oh, just same and same. Okay.
Just
great,
do
great.
one case. Yeah.
Great. Okay. Cool. Thank you.
looking at this problem, it looks pretty straightforward in that I think we have a sphere, we have a cylinder.
Uh-huh.
All else being the same mass, same diameter. Wouldn't it just be a question of which one has the greater moment of inertia? That one is going to reach the bottom, the ground last.
Which one is the lower moment of inertia?
The lower moment of inertia will reach the ground first.
Yes.
Okay, so in that case, then the answer would just be cylinder.
Yeah, unless it's 2/5. I forget that.
I'm sorry. The solid sphere has 2/5.
Solid sphere is 2/5. Okay, and the hollow sphere is 3/5. I don't.
The
really
hollow
remember.
sphere has 2/3.
Oh, 2/3. Oh, okay. Yeah, well,
So
you have to look it up then.
no, I
don't
got.
remember. Yeah. No, you're right.
No, but it's saying like instead of 2 spheres, it's a solid cylinder and a solid sphere.
Mhm.
So the solid sphere has 2/5 mr squared. That's
Yeah.
the moment of inertia. A solid cylinder has mr squared.
Yeah.
So a cylinder doesn't have as much of a moment of inertia.
Mhm.
So
Sure.
in that case, it reaches the ground first.
Yes, but I would actually write the speeds
Okay.
because really what you're saying is the fact that there's low moment of inertia means that when it gets to the bottom, it was going faster, and you have to sort of kind of know that means, of course, it's gonna be shorter. I guess it's kind of obvious, but you know.
Okay, so in that case, we have mgh, but that's going to be the same between both
Yeah.
both of them. 1/2 mv squared. I assume the v is initial velocity.
No, that's the final velocity.
Okay, final velocity. How would we calculate final velocity for it then? For the
With this
between a
equation.
sphere and a what?
We're just with this. That's what this whole equation's for.
Oh,
That's
I see.
the thing we're solving for.
Yeah, you're
Oh,
trying to
okay.
find
Yeah.
Okay, so in that case, we know the value for I because we know the value for m and radius.
Mm.
All right.
Of course, yeah. You have to fill in whichever I you need.
All right. And
This is the only thing that's different between the cases.
and what about omega? That's just r and v. Okay.
Yes.
All right. So in that case, we figure out which v is greater,
Yes.
which final velocity is greater,
Right.
and then we use that to say, okay, since this one has the fastest final velocity, it stands to reason that's
It got there sooner
fair enough.
because it was going faster more of the time, kind of thing.
Okay.
Because technically, we didn't actually solve for the time. Right? We didn't actually anywhere solve for the actual time it takes. That's really how you should do it. But of course, you can assume that if it ended going faster,
probably got there
it
quicker.
got there fast quicker. Like it, you
You
know.
probably reach the bottom first.
Right,
Yes,
because
that's kind of the definition of speed.
it's unlikely that it just gains speed at the end. Like that's not how it works. Of course, if it was not a flat ramp, that could be completely wrong.
Hmm.
Right? The fact that I'm using the fact that the speed is going to increase linearly with height.
Okay.
Well, sorry. Okay, never mind. I'm using something else, but I'm using the fact that it's increasing monotonically is the real way to say it, but it doesn't really matter. So,
Yeah, that's a $5 word.
right.
I don't know if I'm ready for that. Okay, so we're
The
all-
acceleration is constant. That's,
So
I
we're all
guess that's the
happy
correct way
with
to say it.
we're all happy with number 2 then.
And number 3, I think, is the same thing.
Essentially, you
A
have different
solid
shapes.
ball-
Yeah.
Equal masses are
Okay.
released from the same height and rolled in inclined plane, which reaches the bottom first. What happens if you do the same for a solid and hollow cylinder?
There's just different eyes.
Okay.
Different
so,
eyes. Yeah, it's the same. This formula still, right?
So instead of rewriting the same formula, would it be feasible? Would you accept it if we just said, okay, based on the reasoning of problem number 2? See the
Yeah, if
formula?
you found a pattern for the I relationship to, yeah, you could write that. You make sure you write that because of the equation above. We know that lower I course. I think that's right. Don't copy what I'm saying because there's a chance that I'm wrong. But if you just do it out for the first one, you'll see whichever one's higher.
Okay.
Yeah, I mean you can actually do it without it plugging in an I and leave V, and you'll get something with a square root. With a square root, and you get something with like an I in it, and then you can just see if I is lower, then V is higher, right?
Okay.
V final, really, I should say.
All right. I'm happy.
Okay, good.
Yep.
So you want to talk about rotation matrices?
Please.
So I don't know what he said in class because I wasn't there. Because
Wait, yeah, you were. Oh, wait, you.
I
took the
showed up
tests.
late because I didn't know the class was going to be early. I think there was an email. I didn't see it. But anyway, I wouldn't need to be
We were
there. For
taking- we were taking the test.
yeah, that's what I heard. So
Unless you were willing to help us out during the exam.
I was not willing.
Yeah.
Okay, so you didn't miss
Um,
much.
I would just have to sit there. So.
How much
Actually, I
in-
would have been grading your homework, but
How much input do you get on what problems are on here? Just out of curiosity.
on your homeworks,
Yeah.
I can see all the future homeworks.
Okay, but do you get?
I don't get to choose. No. They're all
Oh,
laid out from
okay.
last year. Yeah.
Oh, cool.
Or he might modify them a little bit, but they're. I don't get to choose at all.
Have you considered writing have you actually gone through with writing that book? Revisions to the textbook, and then just give it to professors.
No, he has
it.
that errata.
Yeah.
Okay.
Is that how you say it?
Errata.
It sounds like
Looks like
erotica
that.
or something.
Yeah, that's
it
why-
sounds a little weird, but is that what I think that's how you say it?
ERATA.
But anyway, yes, he has that, and there's a lot of errors in it. But and one of them was anyway. It doesn't matter. It's
Cheaper to do that than just print a second edition.
yeah, or
That's-
rewrite it.
I'm really
Or
just
rewrite.
curious about something something non-physics related. Do you own any non-black T-shirts? Because I feel like every time we see you,
I do
you
know.
have
I
black
wore
t-shirt.
I had a purple one on like a couple.
Oh, really?
Because I remember looking at the videos
Okay.
and remembering, oh, this is the new bit. I looking through the links and I was like, which one is this one? And I own. This is from Uniqlo.
Oh,
I
Uniqlo's
own-
Yeah,
great.
and,
Oh,
Yeah.
I own 10 of these.
Okay.
so
Uniqlo's that like
like a
Japanese
Japanese-
it's a Japanese clothing retailer, and they're like known for like pretty cheap, but like also pretty good quality like clothes.
Yeah, like
It's on
They sell a lot
Newberry.
of like $5 graphic tees. They got a big store in Boston. Yeah, it's really
Yeah,
cool.
there's a bunch in New York.
It's not Primark.
It's not Primark.
Okay.
No. Oh, Primark, I've heard good things about.
Primark is cool. I've got the best pants I've ever owned from Primark.
Oh, really?
Granted, I bought them too big, but they are very comfortable.
now, what constitutes the best pants? Like because they're flexible, because they're
Because they
stylish?
fit well and they're
Because-
comfortable and they look good.
All right, but fit well where
Check.
exactly? Are we talking like legs or are we talking hips?
Wow.
I'm just
This
taking the
All
piss
right,
for
rotational matrices. Stop it.
Anyway, all right. So let's talk about matrices. So I don't know how much you talked about, but I looked at 4.1, and it's relatively.
He didn't. He only,
Oh,
had,
that.
he only had a
I
couple
see.
slides.
Oh, that's from the book.
Wait a minute. We're doing 5.1 for the homework though.
Yeah, it's
Whoa, you're just talking
so
about
so.
just-
There's
oh,
no
wow.
questions in chapter 4. It just said in the thing to read
Read.
4.1,
Oh yeah. Okay.
and he basically talked about. Now I don't know whether you're ever going to need this, but I'll just talk about it for a little bit because
I
I
think,
think it's way more interesting.
so
Than,
you said it's
and the
cool.
other stuff.
So.
Considering we got a second week of questions on chapter 3, it stands to reason we might get
Right.
some delayed chapter 4 questions.
Yeah,
so.
fair enough. Actually, no. I looked in the future, in like at least in the next 2 weeks, there is no chapter 4
Ah.
questions. So he literally might not ever give you chapter 4 questions.
But he might give us a chapter 4 problem.
That's
for the
true. He
next-
could
for the next
possibly
quiz
give you
or
a.
the final.
I literally don't even know what topic because I know you're going to do waves next, and then quantum
but
like
quantum-
wave functions.
The
so quantum
tables
mechanics.
could
But yeah,
certainly-
quantum this semester. Thought
But
you
quantum,
had
you
next
don't
semester.
need rotation matrices. You would need more linear algebra, which
Quantum
is
actually
great.
Quantum actually isn't that bad, is it? It's just all
No, it's not
all-
going to be that bad. No.
It's all nonsense. So
Well,
you
it
can
can be really
say
bad.
whatever
I
you
can't
want.
imagine that it's going to be bad for this.
No, it's going to be it's going to be solving waves.
No.
You know,
No,
it's, there's a differential equation that you have to solve in different situations. That's the whole thing. It's called the Schrödinger equation. It's relatively simple.
And that's like with the wall, the infinite walls.
Yeah,
on
yeah,
both
that's
sides.
what it's going to be. Yeah,
Yeah.
and the answer
Oh.
is a bunch of standing waves. So once you learn standing waves, it's the same thing.
Okay.
But anyway, okay, sorry.
Okay.
Let me get to that.
So,
So
rotational matrices.
yes,
Professor Z made it sound like a rotational matrices. It's not exactly a physical concept so much as it's a technique used to make equations and looking at situations more easily.
yeah.
So like it's more like
Yeah.
a different perspective, not like a physics concept.
It's how you change coordinates. So of course in physics you shouldn't have anything depend explicitly on coordinates. Now you can have things that's a bad thing to say. You can have things depend on coordinates, of course. That's how you do physics. But they should be what's called invariant under changes of coordinates. Meaning like when you do the ramp problems, you should be able to talk about the forces down the ramp and up the ramp. It's not like we can only talk about forces vertically and horizontally, and we just have to break everything up. No, you can just tilt your reference frame and just say there's a force down the ramp and a force perpendicular. That's called rotating your frame, right? And all you have to worry about is the fact that gravity no longer acts in one dimension; it acts in two of your dimensions. But that's fine; just break it up into components. So this is literally the same thing, and this is just a mathematical way to express that, which is I'm going to do 2 by 2 because the 3 by 3 are the same thing, but just bigger. But like for example, this matrix, I'll just show you how they work. Let's say we had a vector AB, right? And that's in my xy plane. So this is x hat and this is y hat, right? Let's say I had a vector AB, and let's say, I don't know, it went like that. So AB means that this point is called AB, the component in the x direction is A, component in the y direction is B. I could also call this A x hat plus B y hat, or they might say I and J, it doesn't really matter. So that's my vector V. Now if I take, let's say I want to do this with, this is called a linear transformation here, right? And let's say I want to see what this linear transformation does to this vector. A linear transformation takes my basis vectors and just changes them. And then the new thing is written in terms of my new basis vectors. So let's say if I'm doing a block on a ramp problem, right, with a ramp like this, my original basis vectors are like this, and I want to basically tilt them like this. So this is the same idea. Now you wouldn't do a matrix for this because it would be too complicated. It's easier to just break things into components. But this is actually a silly example because if I multiply these out with matrix multiplication, I do this times this plus this times this, which is going to be A, and then this one is going to be this times this plus this times this one is going to be B. So obviously this doesn't do anything. So this is called the identity, or it's also called a rotation by zero, right? This is called the identity transformation. I'll call it like a 1. Now, of course, you could do all these linear transformations, like you could make x be much longer, that would be fine. And then all you would get is that the x coordinate gets like scaled down by some factor. So again, that's all I'm doing. I'm not actually changing the vector at all. I'm just changing how I'm labeling it. Where instead of this being the x coordinate and this being the y coordinate, this is my new x coordinate, whatever, after I transform the x vector by this. So if basically, in other words, if I double the x basis vector, I'm just taking half of all my x coordinates. And that would be my new coordinates to the. So I'm just changing I'm keeping the same vector. So if I called this x hat prime, and I called, I'll just double both. So I call this y hat prime. That's this linear transformation here. Right?
Right.
And now, if I do this matrix multiplication, I get. So okay. So this would double this vector. Vector called AB gets sent to a vector called what originally would be called 2A 2B. To get back to my original, I have to divide by 2, basically. Anyway, it gets this little bit of a silly example. But let's do rotations because they're much more reasonable. Because this you would never do something like this because you wouldn't scale both things. And also if you scaled just one, you would kind of mess up perpendicular things, so you wouldn't do that either. What you would do that preserves the things being perpendicular, so your two axes are always going to be perpendicular, and things that are perpendicular are going to get sent to things that are perpendicular, and lengths are going to be preserved. Those are called rotation matrices, right? There's also, you could have like mirror versions too, those would also work, but we're not going to do those because they mess up other things in
So
physics.
in what real world situation would you have to use something like this?
The ramps.
The ramps?
The ramps, yeah, I mean, you wouldn't necessarily have to write a matrix for that. I mean,
Yeah, because then
Because you could just
apply
turn
the
your
sines
axes
and the
into
cosines. Right?
yeah, I mean, breaking things into components is the same thing. But technically,
You're doing a low-level version of this when you do that.
yeah, I mean, you're doing that like one at a time.
Yeah.
This
Yeah.
sort of generally should take you from any vector to any vector. You're generally not like setting up a coordinate axis when you do that because you don't actually care. You just care about forces. You don't care about like specific coordinates, right? You just care about like the vectors. This actually does the whole thing. This takes you from an xy plane to another xy plane where the coordinates are sort of shifted. Anyway, but let's just talk about the rotation matrix. So the it's going to be like cosine. There should be a minus sign on that one, I think, and not that one. But the way I think he writes it like this, which I'm not convinced is right, but whatever. And so if we take a vector, well, actually, let's not do. Let's instead of saying a vector AB, let's just say what does it do to the x-axis, right? Actually, another way to look at rotation, or another way to look at these matrices, these linear transformations, is to say that this column here is the new x hat vector, the new basis vector for the x component. This column is the new y basis vector, right? That's why, remember, the identity looks like this. The new basis vector for the x component is 1, 0. Well, that's just the old one, right? And the new basis vector for the y is 0, 1. That's just the old one, too. So this is the identity. If I change this to a 2, this linear transformation is saying that I keep the same x basis vector, but my basis vector for y doubles. So everything gets doubled in the y, right? Anyway, this, let me draw that here. So this linear transformation, which I'll call r theta, is saying that my new x, so my x originally was here, let's say, and my y was here. My new x component, x basis vector, is going to be, let's say I have an angle that I measure like that way. My new one is going to be cosine theta, and my y component is going to be minus sine theta. So I don't really like this that much. I think I think this should have a minus, but whatever. It should work either way, I guess.
So how are you multiplying these?
Oh, how do I multiply matrix by a?
Yeah.
So I do. It's actually the dot product of this row with this column is the first entry. So it's going to be cosine times 1 plus sine times 0. And then this is going to be minus sine times 1 plus cosine times 0. That's why you can see that the x vector was sent to the first column, which is what that arrow means.
Isn't cosine of 0 0? Sorry.
I'm not
0,
taking,
1?
no, I'm just multiplying.
Oh, I see.
I'm not plugging in theta at all.
Okay.
We could plug in theta as 90 and 180. That actually would probably be a good thing to do. But, yeah, well, let's just see how this works out now. So, okay, I got it. So, now, why is this not? I think. So if I do this, oh, this is theta. Oh, I see. So this is saying that my new x vector is going to be what am I doing? Can I see in the book? I'm just bothered by this minus sign. I really don't like it. Yeah, because I think it should go that way. That's where they have it.
Do you need to transpose that 2 by 2? Perhaps.
No, because I mean that's what I'm thinking, but the way they've drawn it. Right. All right, let's plug in some numbers. I know I hate to do this. I just explained this to what's her name? Anna, is that her name? She's usually here. Anyway, the other day in office hours, and I found a subtle mistake, but I can't remember where it was. No. Anna Maria, yeah. A subtle mistake between the picture and this matrix they drew, but I can't remember what it was. So let's just plug in some numbers and maybe I'll figure it out. So if we plug in theta equals pi over 2, we get what? This is going to be called r pi over 2. This is going to rotate, I guess this way according to the picture, by 90. So it should give us this. And then we get, well, cosine of pi over 2 is 0, right? Wait, is that right? Yeah.
Mm-hmm.
And minus sine of pi over 2 is going to be minus 1. Sine of pi over 2 is 1, and this is 0. So it's going to give us this. That's saying my new x basis vector is going to be 0, minus 1, which is going to be, this is what I thought. It's going to be down here. 0 minus 1 is this vector here, right? This is x hat prime. And my new y vector is going to be, this is the original x vector. So it's going to be here. So what I've done is rotate this way by 90 degrees, right? That's where this picture shows this rotating the other way.
So then, perhaps because you've denoted those 2 columns in the 2 by 2 as like the new x and y. So then you can think of the rows as like the first one is like compared to x and the second one is like compared to y based on that description, right?
Not always. So that's true in this case.
Oh, okay.
Yeah. So that's this matrix is very like symmetric looking, kind of.
Mm-hmm.
So, but generally you can't really do that.
Oh.
You can always look at the columns as the new basis vectors.
Okay.
So, yeah, but it's very tempting to say that as well. In 3 dimensions, the one they do is just this with another, like the 3 by 3 identity is this, right? Mm-hmm. Right? And if we just replace this here, if we replace this upper 2 by 2 with that, we would get a 3-dimensional rotation where we just rotate like a big column, where the z-axis doesn't change anything. So that's what they're doing. That's the exact example they have in the book. I didn't want to do 3 by 3 because it's just annoying to write, and it's not more interesting. We can also, of course, do a 3 by 3 where we, if you take a globe, and you rotate, so you have the north pole is the z-axis, the north to south pole is the z-axis. If you rotate it in like the longitude lines, that's just like this. But if we also rotate it, if we say when there's another angle, we're going to rotate it like we're going to tilt it downward, so tilt the North Pole, that would be another angle. And that would be, we would have to use called polar coordinates. And to write that like this, we could write a 3x3 with those and we would have a ridiculous, there's so cosine signs everywhere. There's actually cosine signs of theta and cosine signs of phi, which is another angle, which is going to be the angle from the top. So that's how you do.
Oh, like with spherical coordinates?
Yeah, that's how you do spherical coordinates.
It gets really gross.
It's really annoying. So you would never, I've literally never even seen it. Well, I've seen it on Wikipedia, but I've never written it at all.
In your nightmares.
Yeah, because you would never do anything like that. You could do polar coordinate integrals and stuff. Those are actually easier than writing the matrix. So I don't really know what more. I would say if you know, it would probably give you this. And if you just plug in like the main ones, like let's say we plug in, let's just do another one. Pi gives you pi, which is going to be, well, cosine of pi is -1, and cosine of pi is also -1, and then 0, 0. So this would say that our new x-coordinate would be just the minus of the original x-coordinate. So our new x-coordinate would be this way, right? X goes to x double prime, I'll say, for this one. And then the new y-coordinate is just the minus of the original, so it would be down. So of course this rotates you like this. Note that this is not the same. Well, here's a kind of another fun fact. It's not really that much fun, but it's kind of interesting that if we take this matrix here, and this is probably beyond anything you'll need to do in this class, but if we take this matrix here and square it, okay, square it just, now, of course, you could square it by just writing it next to it and doing the multiplication. That's boring. We could also just say, squaring it says that you're doing this linear transformation once where you go like this, and then you do it again. And again just means I'm taking whatever vectors were here and rotating them here, but that, of course, just pushes these back here. So this squared is the identity, right? Now, the thing is, though, that the interesting part is that this is not the only matrix such that this is true, right? We could also have a matrix if I write this. This would also be the identity. It's not the same as this. And this, let's think of, well, what rotation would this be? Because I somehow said there's another matrix that looks like a rotation matrix that you can do something and do it twice and get back to the original. Well, it seems like there should only be the one. It should only be the 180-degree one. You shouldn't have more than one. So what is this? Well, if we look at this, that means that sine has to be 0. Okay, that's fine. But that means that, wait a minute, cosine and cosine have to be 1 minus 1. That can't be true, right? So this is actually not a rotation matrix. This is a matrix that mirror flips you, and you can see it takes the x-coordinate, sends it back to itself, and it takes the y-coordinate and mirrors it. This is actually a mirror reflection across the x-axis. Now, of course, if you do that twice, you get back to the original, but it's not a rotation. You could also do the same thing with a minus sign here, which would be mirror the other axis. That's also just a rotation of this. And this.
Oh, I see. Okay.
Now,
I took a second to visualize it. Okay.
Yeah, no, these are all very visual. Of course, all of these you could do matrix multiplication, just like we did with this, but with another thing, and you'd have a 4x4. But of course, these are all, now I'm getting way off track, but these form what's called a group, which is an algebraic structure that a lot of people have studied for hundreds of years, and it's incredibly interesting.
But these sarcastic.
No, I'm not being sarcastic. This is very interesting.
Stop talking about math, you know he's not being
It's
How so?
it's called group theory.
Okay.
So,
How is group theory interesting as opposed to the boring stuff?
well, because there's a lot more. There's things like subgroups you can talk about. So for if we take this is called a discrete group. The rotations form what's called a Lie group, which is a sort of infinitesimal group with infinitely many elements.
Okay.
So the point is that, well, the point I was trying to make with this is that the set of 90-degree rotations, so there's 4 of them, right? There's the identity plus 3 rotations, plus the mirrors form a group such that it's isomorphic to like all these other types of groups. Like if you take all the symmetries of like a square, take a square and you find all the possible things you can do to it, such that when you combine two, you get another thing. That's the definition of a group, is that it's closed, meaning if you combine two of the rotations, you get a third thing that could be a rotation or reflection or whatever. It's like what I was saying, if you combine this, which is a mirror flip along this axis, with a 90-degree rotation, you get a flip along the other axis. So that whole set of 90-degree rotations and 90-degree, not 90-degree flips, but mirror flips, and actually diagonal flips too, you could do. You could flip along the diagonal. That forms an 8-dimensional called a group, and you could write their entire algebra with like some of them squared to the identity, and some of them, like the 90-degree rotation squares to 180-degree rotations, right?
So
Yeah.
in that context, are they a group because the relation between the x and the y is always the same, such that if we're looking at, the angles on the board, the x is always the one on the left?
No, because when we do the mirror, they
the
don't
mirror
they
is
flip.
part of the group too.
Yes, exactly.
Oh,
and we
okay.
could take the subgroup such that is true. There's a subgroup where the x is always on the left or whatever you want to say, right? On one side. That would just exclude all the reflections. Then we'd have a actually pretty simple group where it's just the 4 rotations, the 3 rotations of the identity. And there's all these things you could do with it. You could form. Anyway, I don't want to get into it, but you could form what's called a quotient group.
Well, you do, but we can't right now.
Oh, I do want to get into it, yeah, but there's no point. It would distract you from doing less interesting things. No, I'm just kidding. But the other things are interesting, but this is very interesting too.
There's no group theory.
You could look up if you want to look up group theory. I would look it up. It's very similar to, there's a group called D4. I think it's called D4. It's called the dihedral group on the square. That's very similar to this. You can also look up group of rotation matrices.
So, are you studying group theory out of interest, or have you invested
Yeah.
part of your?
Oh, I took it as an undergrad and grad student, kind of. But
Okay, so familiar then.
it's very important in high energy physics, yes.
Interesting.
Because you have to deal with what's called, so this, I always said this is a Lie group because it has an infinitesimal parameter. So this is not a Lie group because it's just a set. It's a finite set of things that you multiply together and you get other things in the set. That's a group.
Okay.
That's called a finite group. This is called a Lie group, which means, or a sort of, which just means that there's a parameter theta such that it's a real number. So this group is topologically equal to the circle. Okay. This has the shape of the circle, and you could just say, well, it's just like it has one parameter, an angle. It has one parameter that gets back to itself. So of course it's a circle, right? Topologically, it's one number that goes back to itself. It has to be a circle.
Okay.
Anyway, so this Lie group, this doesn't have any reflections in it. This one doesn't. But that's topologically a circle, and so what was I saying about it? I forgot what I was.
Yeah, you did lose me, but I was following.
I forgot. Who did you ask me something?
He did.
What did you ask me? I forgot.
My earlier question was just, what was it?
Why is it more interesting?
That's but before that.
Oh,
He said something about. I was answering it with something about a Lie group, but I forgot why.
The last question I remember asking was, how do you multiply those two particular matrices of different sizes?
Oh, I could
From
show
there-
that too.
Yeah, and from there we went and you started going into different. You tried. I also said, "What's a real life example?"
Yeah.
And then I also went and I asked, and then you started plugging in different numbers.
Yeah.
And then
I
I
could-
think after you decided what direction it was being rotated, and we started
Yeah.
going into group theory.
Yes.
Is that about right?
No, that sounds good.
Okay, so
Um,
where do we go from here then?
Well, what do you want? What do you want me to do, Carol? I'll let you decide where to go now.
I have my say. It's your turn.
Well, I could talk about just multiplying matrices.
Well, I was sure. Yeah, I asked him about rotational matrices.
Yeah, but I asked my questions
Oh,
on
go
rotational
ahead.
matrices. Okay, who? It's
I
your
will.
turn.
I'm
You
here
just
for the
did.
ride. I'm having a good time. I'm learning a lot.
So let's do the multiplying one because he's probably gonna do something.
Yeah, that
crazy
would
to us
be-
like that.
Yeah. So let's just multiply. Let's do an explicit example where we multiply the this is a R180, sorry, this is I'm gonna use degrees now. You shouldn't probably use degrees, but I don't want to keep writing pi.
Is there a reason
I'm
we
often
should-
surprised that more people use radians. I would think that degrees
Yeah,
would be
right?
more.
A little
Easier
more
to work
intuitive because we just
Yeah.
use them all the time.
Yeah.
Why wouldn't you use degrees in this?
Yeah, I don't know. Well,
So what's this?
in
R1?
principle, radians are much more. Much better because they don't have a dimension. Technically, degrees are sort of a weird unit. Like when you do those unit things,
Mhm.
radians are nice because they have no units. Because the definition of a radian is a ratio of a length to a length, and so the units are 0 or 1. I mean, anyway. So this is if I take the rotation matrix that he gave us and plug in theta equals 180,
Okay.
right? Degrees. And then I'll take 90, and let's see what this is. Well, this is what was it? This was minus sine. This is going to be -1.
The first one's
That was
R1.
this, right?
Okay.
So let's just do this multiplication. Now, of course, what we should get by some group theory, I'll stop talking about group theory, but this is how I would write it. This is R270, of course. Right? This should be, because this means composed with. This is, I'll put times. It just means that we do them on top of each other, which is what this is. So now if I multiply these at the same time, well, let's see. So the first element, so this is going to be remember, this is a 2 by 2 matrix, and this is a 2 by 2 matrix. Okay? You can only multiply matrices. Well, first of all, you're never going to see things that are not square matrices, except in like MATLAB.
Okay.
I really don't even know of I literally couldn't give you a reason why you'd use a non-square matrix other than to compute a big thing. In physics, everything's a square matrix. Anyway, but these inner terms have to agree, at least. This is the minimum, that these inner numbers here have to agree. This has to be a 2, this has to be, this has to be the same number as this. Otherwise, you can't multiply them, it doesn't make sense, there's no definition. Then the output is going to be whatever this times this is. So the output is also going to be a 2 by 2. So if we had an A times B matrix multiplied by a B times C matrix, we would get an A by C matrix. The first number is always the rows, and the second number is always the columns. So anyway, this is just the general thing. And if B is not B, then you can't do it. So we're going to get a 2 by 2. The first entry here is going to be the first row. So basically, you can say this is the first row and it's the first column. So I'm going to take the first row here and do the first column here. You always there's 100% of the time you will always use the rows of the first matrix. Whether it's a vector, whether it's anything else, you will always use the rows here and the columns here. There's never a situation where that's not true. Okay, so it means if you're wondering like, wait, should I do the columns or whatever? Like this is the first row, first column, but I don't know which is which. Always do the rows here and the columns here. And so this times this plus this times this is 0. Right? This times this is 0 plus this times this is 0. So it's the dot product. So this is like the dot product of row 1 dot column 1. That's how I would say it, right? This is row 2, still column 1. So it's the dot product of row 2 dot column 1. And you know how to do dot products, right? That's like, it's just yeah. So row 1, column 1 has dot product like that. Now you could write, don't be embarrassed if you'd like to write them all out. That's fine. Like when you're doing them. Some people find that easier because in your head, especially if it's a 3 by 3, it gets very easy to like forget. Or, I mean, also what you should always do is put your fingers, and again, it's like going to seem a little silly, but literally put your fingers on the things you're doing because it's incredibly easy to like get mixed up with this whole thing. So this is 0, right? Row 2, column 1 is going to be row 2, column 1. Again, just the reason that it's always rows first, everything you talk about with matrices is always rows first and then columns, right? And so the first matrix is always going to take rows as the input. So that's another way. Anyway, so this is going to be 0, 0, 1, minus 1 times minus 1 is 1. Okay? The next one is going to be row 1, column 2. So row 1, column 2 is this. 1 times minus 1 times 1 is minus 1, or 0. And then this is going to be row 2, column 2, 0 plus 0. This. So this, by just some what what a 180 degree rotation and a 90 degree rotation is going to be. It's going to be 270. Technically, I would call that group theory, but whatever. This is R270. It's also, of course, this should be equal to R minus 90. If I rotate the other way by 90 degrees, it should be the same as 270, right? That's what it is. So we could check that by just using, remember, it's cosine theta minus sine theta, cosine theta. Well, what's minus 90? Well, cosine of minus 90 is 0. Cosine of minus 90 is 0. Sine of minus 90 is minus sine of 90, right? This is minus 1 again, plus 1, and that's the same as that. So this is just rotating by minus 90 degrees. Of course, that's the same as R270 because, and of course, we could just plug in 270 as well. It's the same. It'll be the same thing.
So when we talk about like rotation by degrees, is it going
Yeah.
counterclockwise or clockwise from the standard?
That's a great question. According to the picture, it really, really, really should be this way, because that's the way every angle is measured. And that's the way the picture says. The thing I'm not sure is that what this is written, how this is written, does not seem to agree with either of those. So I'm not sure.
Okay.
I would look up it's possible that there's something silly that I'm missing, like, oh, it's just the angle from the new one to the old one, which is backwards or something. I don't know. I really don't think that this picture matches.
Are you going to be contributing to Professor Z's erotica?
I have some ideas.
That was a slip. My mistake.
I don't think you're sorry enough.
Yeah.
What would you like me to do? You want me to write an apology note?
I don't know.
Okay, I'll find something.
I
Okay, so
I would look up the point is I wouldn't think too much about this. Not think too much in terms of matrices, but I wouldn't worry too much about like doing problems with this because the ideas are relatively simple. To do problems with it is actually incredibly difficult, as you can see from this diagram.
Yeah.
Like the axes are like this now, and it's like this distance versus this. It gets very, very confusing, and you almost never need to do it because in real situations, there's always an easier way. Like the ramp problems. You don't actually need to like do a coordinate shift. You just need to break things into components.
Yeah.
Which is
then just use
formally the
cosine
same
and
thing.
sine, right?
Exactly.
Okay.
This matrix just supposedly does those cosine sine things for you, but if you know how to draw triangles, you can just draw triangles. And I would do that because that's really how you verify it.
I imagine it could be useful in a situation where you would have a number of different components. Like so, instead of like a 2x2 matrix, you'd need like maybe 4 or 8 or 12, like in components.
That would be in 12 dimensions.
Yeah. So in that case, oh, I see.
You won't do any problem in 12 dimensions.
No, fair enough. I wasn't thinking about that.
You might do things in 11 dimensions if you work on string theory.
Yeah.
But anyway.
I don't think that's for me.
Me either.
All right. So this is basically just rotation matrices is basically just treating the unit vectors such that. Okay.
Yeah, it's just
another technique then. It's
Right,
not
and
like a physics concept or a technique we'll need to use for a particular.
it's a
branch
math
of physics.
concept.
Okay.
It's a way to treat coordinate systems.
So
So you're right that if you basically another way of saying the idea behind this is saying that you know how to take the entire coordinate plane to a new coordinate plane if you know how to take the basis vectors to whatever your new basis vectors are. You don't need any more. So every vector can be expressed in every other coordinate basis. You just have to figure out, it's all just like how many x's and how many y's.
Because the base are the most fundamental building blocks you could use.
Exactly. You could literally will construct your entire coordinate system from your basis vectors. So if you just write 2 columns of how your basis vectors transform, that becomes a matrix that's called a linear transformation that acts on any vector you want and takes it to that new basis. I would, if you really want to learn about this, the interesting parts. Yeah, I almost positive you will never need to do any problem with an actual rotation matrix where you literally multiply it and like write x prime equals cosine x. Like I literally don't think you'll ever need to do that. But I've never needed to do that. But if you want to learn more about like the intuition behind this, not the group theory stuff, that was just me, but the actual like what a linear transformation is supposed to do.
Mhm.
If you look up, said this at the review session like a couple months ago or a month and a half ago, or whatever. If you look up 3 Blue 1 Brown on YouTube, 3 Blue 1 Brown linear algebra. I think it's called Essence of Linear Algebra. This is fantastic. It's a playlist. It's like probably 11 videos. The later ones you probably won't be very interesting to you. They're like about determinants and stuff. If you've done a lot of stuff with them, they might be interesting to you. But if you've never seen them, you don't need to. But this has a lot of this basically does what I did, but way better. At least the first ones. They literally give you a good intuition of what a linear transformation is supposed to do.
Do you know why it's called 3 Blue 1 Brown?
Yeah, the guy that makes it was like a math student, but he has like this condition in one of his eyes that's like it's like 3/4 blue and like 1/4 is brown.
Really?
You don't see he doesn't have his face in the videos,
That's
but,
so cool.
but he says that, yeah.
That's so cool.
Yeah.
I once knew a guy with a similar thing from camp, except his was brown eyes with like a little quarter of green in them.
Oh,
Yeah.
you should start a YouTube channel
Wild.
on math. But he's I don't know what he does. He was like a math grad student and now he hangs out. But anyway, all of his videos
He's
are
just showing-
fantastic.
We're
He's
top.
literally one of the best YouTube channels I've ever seen. But specifically, this is very good.
I had a little linear algebra senior year when I studied computational fluid dynamics,
Yeah.
and I'll be honest, I don't remember any of it, but it was a bitch.
Yeah. No, this is
Fair.
a great, like, good intuition building
Yeah.
because you don't do problems. It's not like Khan Academy. where
No.
this is literally how to think about it.
Yeah.
And even if like and I was like, all right, let's just see. Like, I think I know linear algebra. And still, I was like, this is really interesting. Like, I don't need to use it for anything, but it's just like anyway.
She
So.
basically set us up the entire semester to do our project, which was one problem,
Right.
and it was ridiculous. It was a cylinder in a wind tunnel, and we had to both simulate and calculate it. And I mean, it was like 4 pages of calculation.
Wow.
I don't remember how.
I actually know what your next project is going to be.
What? Is it cool?
It's 2 cylinders.
It's
Huh?
I don't know what I'm supposed to tell you.
It's okay, you don't have to.
It's about I'll give you a hint.
Okay.
It's about a harmonic oscillator.
Okay, I thought for a second you were going to say 2 baseballs. That would have just
Yeah, two.
How will the harmonic
2
oscillator
baseballs.
behave at Coors Field versus Fenway?
A harmonic oscillator was shot in Coors Field.
David Ortiz hits
Yeah,
a string
yeah.
with a baseball
Anyway,
David Ortiz hits a harmonic oscillator with a baseball bat. What are the discuss Young's module needed for the harmonic
Right.
oscillator
Did you
to
guys-
not break
Did you
under
guys have to
strain.
take a vibrations course undergrad?
It might have been a subject, but
One
for one of
I
our
didn't take a
classes.
separate class.
No, we had to. So go
I
ahead.
took vibrations and waves.
This was just
class.
vibration.
Yeah.
Sounds like you're pretty shaken by it.
Yeah, it screwed me up.
You got it. Thank you.
Thank you. I got it.
All right. What do you want? What do you want to do now?
Um,
Oh, I know what I have a question.
Yes.
So, can I draw my?
Sure.
Okay, so basically you had, like just as one example, right?
Yeah.
You had this, and you said X hat, Y hat, right? The columns are
Uh-huh.
always represented by this. And I said, could you think of it as like X hat has this many of the original X and this many of the original Y? And you said that's not always true.
Yeah.
Can you think of an example where that's not always true? That we might be able to visualize? Because this
That
seems
might
like
be
the
true,
last
now that I
key to
think
make
about
it
it.
fully intuitive.
Yeah. So I think what you're. So if you have a matrix. Well, okay, so what does this do? This takes x hat, y hat, and sends it to x is now 0 minus 1, and y is this, y prime is that.
Like the way I would read it, if I put it in a sentence as x hat has 0 multiples of x and -1 multiples of y, and y hat has 1 multiple of x and
yes.
0 multiples of y.
Okay, then yes.
Oh,
Then you're right.
okay.
Okay, yeah, you're
Alright.
right.
Cool.
The only thing I was worried about was, the only reason I said that's not always true is because I was thinking that what you were talking about is like how to undo it, and how you would undo a linear transformation. I know, I guess you weren't.
Well,
quite
would
asking
we
this.
like using the inverse or something?
You'd use the inverse, which is not the same as the transpose, which is what I
Yes.
thought you were saying.
Yes.
So of course, most matrices do not. This is a stupid example because this is itself, but for most matrices, the inverse and the transpose are not the same thing.
Right. Yeah.
So, but what you're saying about the copies, that is true. So, however you're thinking about it, I believe is right.
Cool.
Yes. The slightly different thing that I was thinking about was to undo it, to make another linear transformation that undoes it would not just be like you flip it and you call this x hat and this y hat. But you're right that yes, it's this many copies of x, this many copies of y. You're right.
Cool.
Okay. Yeah, in case you want to know, the transpose is if you just take the matrix and just flip it on the diagonal. Just so you know, that's the definition. And then the inverse is another matrix such that if you multiply them, you get the identity. Anyway, those are, in general, the transpose is very easy to find, because you just do it. The inverse is generally very hard to find, because you'd have to, it's not obvious what other matrix there would be to multiply to get the identity. Sometimes they don't always exist either. Some matrices don't have another matrix to multiply to get the identity. Like, for example, the zero matrix has nothing. You can multiply by all zeros to get the identity. Because the zero matrix is a little, well, it's, okay, now I'm just rambling. I'll just,
Sorry, keep going.
please give me something else to talk about. But the zero matrix has, what this does is sends the x unit vector to 0, and the y unit vector, I mean, I can even do this. Keeps the y, well, actually, it makes the y unit vector x, but it kills the x vector. That means that it sends every vector I put in, AB, every vector in the plane I put in, it collapses to a line. So an inverse would be a thing that takes the line and expands it to a plane. That doesn't exist because there's not like if I take everything and collapse it, what this is doing, I'll do this, it's a little easier to think about. This collapses everything to the y-axis, right? Takes all x vectors and collapses them to 0. So that means that any vector like this, it's going to collapse to a vector like that. And everything is going to be in this line. Now, how do I undo that? How do I take this vector and send it back? Because many vectors, all these vectors, get collapsed to that point. So there is no way to undo it because I don't know where it came from. If I just give this vector, I don't know where it came from. So there's no inverse to this. The inverse would undo whatever I did. But anything that collapses one of the dimensions is called a degenerate linear transformation. And this is and actually there's a mathematical determinant you could figure out that if it's 0, it's called a degenerate linear transformation, and it takes one of the dimensions and collapses them. And you cannot undo that because you can't get back that new dimension. Anyway, it's a whole called the rank if you want to look that up too.
Oh, yeah.
In that thing,
The
it's called the rank of this matrix. If this rank of this matrix is actually 1, okay. If it's 1, that means the rank means the number of dimensions of the output. Okay, the input has 2 dimensions, because I have to put 2 things here. The output only has 1 dimension. So anytime the rank is less than the dimension, that's a theorem. But anyway, if the rank is less than the dimension, there's no inverse, it's degenerate.
What got me in linear algebra was the master theorem, is how it was expressed to me, where it's like the 12 plus things that are all like connected to each other.
The who? What?
I don't know. The way it was taught to me, and so the way it was taught to me freshman year is like it was this thing my professor called the master theorem, and it was like a series of like 12 plus theorems that are all like interconnected with each other.
Oh,
So
okay.
like if this thing is true, then this is true.
Yeah,
and
yeah.
It was a lot.
Huh. I've never heard that name, but
Oh, okay.
that's probably something important.
But it has things like involving like the rank and like
Yeah.
transpose times A times H.
Exactly, yeah. It's called the rank nullity theorem.
Could be.
Anyway,
That sounds cooler.
yeah. Anyway, all right. So what else? Whatever.
Right, so for Young's modulus,
Mhm.
Would you mind going over that? It's like 5,000 foot overview.
Yeah.
Like just the broad strokes.
So it's like here. So I don't really know anything about it. I mean, I know what's in the book, and that's like basically it because we don't.
Can I take it? I might be able to take a stab at this and help you explain.
Sure.
Where did I start writing it down? So my answer. So basically, what I'm saying is Young's modulus is a quantification of the amount of stress applied in a certain direction to linearly strain a material by 1 unit of measurement.
But isn't Young's modulus, doesn't that vary from material to material? Or,
Yeah.
Okay.
Mhm.
And does shape also have an impact on it? Not just the diameter, but it's like would a cylinder,
No.
a cylinder and a sphere of the same material also score differently on Young's modulus?
They should
Radius
not.
being the same?
No.
They should not if the cross-sectional area is the same.
Okay.
Of course, a cylinder has a very thin edge, and so you say sphere or like
Like would a cylinder and a sphere with the same radius?
Well,
same
a sphere-
cross-sectional area?
a sphere you wouldn't compute with this because what's the length of a sphere? You sort of can't. It's not quite.
Fair enough.
So if basically it applies when all these things are well defined is how you would say it in math.
If you have a smaller cross-sectional area, you're going to get, with the same amount of force, you're going to get to that strain much faster in a smaller cross-sectional area, right?
Yeah.
Right?
Uh,
Now I'm confused myself.
yeah. So
So
this is
same force, you, go ahead.
well. So this has units of pressure.
Yeah.
Pascals.
Stress, yeah.
Actually, a way I would think about it, well, a way that's easier for me to think about, which may not be easier for you, is with the three-dimensional case first, because if you know from chemistry, like Boyle's law,
The relationship.
don't-
between-
law.
it doesn't. You don't have to remember Boyle.
That's like a
but
proportional.
that's
something to do with proportions, right? Which one is that?
that's this. This just says that if you squeeze something, it
It's gonna
gets
have an
smaller.
impact on the volume.
Yes. It's a little bit of a stupid law, I think. It's a little bit like, I don't
Nothing's
know,
as
like,
dumb as the reflexive property.
No,
of
Exactly,
it's
exactly.
The something Hasselbalch law. What was it again?
I don't
From
know.
chemistry. Basically, these guys they just rewrote a formula that was existing for like 40 years already.
Yeah.
And they got a Nobel Prize for it.
There you
The
go.
something
Research.
Good way to get them.
The something Hasselbalch law.
This,
It's gonna
That's
bother
funny.
me now.
so I would say, for me, the easier way to think about it is that there's some pressure. This is bulk modulus, right?
Yeah.
If you give some pressure, there's some amount that the volume responds. It can be very stiff, so you can put it under water a lot, and it just won't, like sand or whatever. It doesn't compress very much. Or it can be like air, where it kind of compresses a lot underwater. So I would say, this is like pressure, and this is like the change in volume. This is the bulk modulus. This is exactly the same, but a one-dimensional version. This is saying that if you apply a pressure in one dimension, you're only considering the force is only in one dimension. This, of course, pressure P here is, it's the same thing, but it's technically force in every dimension, right? Over the cross-sectional area of the whole thing, or the surface area, I should say. But this one is just in this one dimension, how much is it expanding or compressing?
Yeah.
It's a one-dimensional change in volume, essentially. Still a change in volume, I guess. And this is the pressure in that one dimension. And this is just how it responds just in that one dimension. So Young's modulus and bulk modulus are identical. It's just they're at different dimensions. The other one with the other, I can't remember. These are all, I hate these. The shear one, the shear modulus or whatever.
Yeah.
That's a little bit different. That's actually not one of these. That's not a two-dimensional version or anything.
It's part of the homework. You over that?
Yeah,
Shear, please.
so the shear one, one of the things that's so annoying is that they use, the way they write the variables is not different at all. They use epsilon for like all of these things.
Yeah.
Okay, let me. What's the other letter? What's the? I don't
They
even,
use
G.
G.
What do they call it? What's called G called the shear modulus? Is that what it's called?
Shear. Yeah. So G is called the shear modulus.
Okay.
Actually, what they use is, they use is it gamma?
Yeah.
Oh, the angle. Yeah.
It's not epsilon. It's gamma.
Yeah, it's gamma. The angle.
Well,
shifts.
so they use an epsilon
wait.
that's like a shear epsilon, which is delta x over L.
Yeah.
Okay, let me let me start over and try to say it a little more clearly.
Okay.
This is a one-dimensional version of this, saying that if you squeeze something or stretch something, it gets smaller or larger.
Okay.
And how much does it get smaller or larger versus how much you squeeze it is the Young's modulus and bulk modulus, right? This is slightly different because this is saying how much do things bend. This is force per area, the same thing, right? I think this is,
Yeah.
Okay.
Yes.
It's the force per area, but it's not. It's the force. Like if you have a rod, it's the force applied this way.
Perpendicular.
Yeah. And this is how much it sort of bends, how much like the top bends, I guess. Like
Displacement.
actually, sorry, it's not. It's not.
The way I see it visualized is like if you broke it up into chunks and they all like shift like a staircase.
Exactly. You're right. That's how I should draw it. It's
Yeah.
really like this. I shouldn't say it's bending. It's more like you're pretending it's actually tilting, like a parallelogram.
That's shear.
This is
Mhm.
shear. This is delta x. This is the length. This quantity is the shear. The shear. Is that what it's called? I don't remember. Anyway,
Shear stress.
shear stress. That's I was thinking that's right. Yes, this is the shear stress.
Shear strain.
strain.
Shear
Shear
strain's
strain. I'm
epsilon.
sorry. You're right. This is the strain,
All right.
and this is the stress.
Thank you.
So
And so hold on. So this is slightly different than those two because this is not the same dimension. So that's fine. And now, yeah, that's fine. So you could do this, but what you could also do, which they do in the book, actually, this is sort of not, I meant to draw it like that. What they could also do is say that this angle here, so if I take the left edge and I take the angle that it tilts at,
That's your gamma.
that's gamma. Well, if I say, like I did just in trigonometry, tangent is going to be opposite over adjacent, right? Which is, so epsilon is actually tangent of gamma. Now the reason, then the simplification they do is say that, well, whenever I'm considering this, I'm not actually considering like very large gamma, right? I'm not considering like gamma equals 45 degrees, right? That would be kind of a lot.
Mhm.
So what they do is say that tangent of gamma, I'm going to take the Taylor expansion. The first term in the Taylor expansion is gamma, which I guess you could solve for. You could also say that because tangent is sine over cosine, and the first term in cosine is 1, and the first term in sine is gamma. It's like gamma. Okay. None of these equal signs mean equals. These are all mean approximately.
Okay. Thank you.
This is equals. This is actually equals, but now this is not a good way to do it. You really shouldn't say that. You shouldn't divide by approximations. That's actually never a good idea, but it happens to be right in this case.
So the difference between shear, stress, and strain. So stress would be applying force over a certain area.
Yeah.
Strain would be stretching something or
Or
compressing something.
compressing something.
That area is still your cross-sectional area.
What's
That area in shear stress is still your cross.
The area, yeah, it's the surface over which the force is being applied to. The only difference between the only difference is that for Young's modulus, it's you're looking at the change in the same direction that the force is being applied, and with shear, you're looking at change in the direction perpendicular to where the force is being applied.
all right. So
The area in both cases is just the surface along which the force acts. In a sense.
So in that case, how would we describe the properties of a piece of rope then? Because since it can pretty much get moved around, swung around anywhere, does that mean that it would have a relatively high strain capacity but a relatively low shear capacity?
Well, I think you could just approximate are you saying like the rope because it's like different strands and they're all wound together? Is that kind of why you're
exactly.
confused?
Like it's very flexible. You can. Push
I
it,
think the
pull it,
best
push it.
approximation you would do is just treat it as like a simple cylinder with like a cross sectional.
Yeah, and you could
That's probably the most reasonable thing you could do.
I mean, as long as you know the cross section. I mean,
You could break it up chord by chord. but,
it
like, why
depends.
would you
I
do
would think about the situation, the problems, more than the abstract. All these, because you'll very rarely have both of these at the same time. If you're hanging something from a rope, you will only use this.
Yeah.
There is no bulk modulus because there is no force going in all dimensions. Right? There's no volume that you care about.
Or if you're like slicing a rope with a sword, then it's
Yeah.
only shear.
Yeah.
So in this
Exciting.
particular instance, the horse is a sphere.
Exactly.
Yes.
You
No,
said
so that case you'd only use this because you only care about the length. That's the only dimension that's going to change, right? It's not going to go side to side because you're hanging.
that's what you meant. Okay, that was my question. Go ahead.
And then this, you do care about the stress, of course, because you always do. But and then there you would need the Young's modulus of the rope. You would not care about this at all in a hanging something from a rope.
Right.
It sounds like the word in Westworld or whatever. Like horses and hanging. Anyway, but like the problem in the book, the one problem was a thing hanging from a rod. Now, if you looked at that and you thought, wait, I need to know all the things about steel, you'd be a little distracted because you actually never need that in that problem, right? In a problem where you need this, you'll probably only need this. So you'll never need both. I don't want to say that because I don't know, but you'll almost certainly not need both at the same time. Or if you do, you can break them up into separate problems. But they're completely separate quantities, and they're related to separate sort of. This sigma and this p have the same units, but they're not, and they're the same sort of type of thing, but they're not equal to each other in any situation.
Is there any way to calculate or try to approximate Young's modulus, or is that?
This is an approximation. Already, all these are approximations.
No, I mean like the value for E, proportionality.
You can test it.
I know
you would have
by
to test
testing.
Okay, so it's inherent to the material itself. You have to
Yes.
test
Material
it.
properties.
Yes.
Yeah.
This is inherent only to the external stimulus, for lack of a better
The
word, of the
circumstances surrounding what you're doing.
exactly. This has nothing to do with wires. This is only to do with things you're acting on wires with. Just like this has nothing. This is only has to do with water pressure, for example, water. This only has to do with forces applied, right? On the right side, this epsilon and this delta V over V and this epsilon here only has to do with the material's response, right? Therefore, this E and B and G all have to do with the ratio between them. How much can you input on something versus how much does it respond? Does that make sense?
Yes.
So
Yeah.
that's a good, like, it's a very good separation of sort of situations here. Like, you have the input, the output, and then this is the relation between them. And of course, the relation depends obviously on the material. Yeah.
Going back a little.
Yeah.
When you were drawing out the rod and explaining the relationship of shear strain.
Yeah.
And you said you wrote down delta X over L, and you said that's different units than strain than longitudinal strain. That threw me off because you were like, "Oh, it's different units." So I'm like, "It's a ratio." What do you mean?
Oh, no.
You meant just displacement of.
Sorry, I should.
Okay.
I didn't mean.
I know. I
shouldn't have said
understand it now, but that's what you meant.
Yeah. I shouldn't have said different units. If I said that, I was
like,
wrong.
What are you
No.
talking about?
It is not different units. You're right. It's exactly the same units,
Yeah.
but it is different, sort of in a fundamental way, because you're not considering this is compression,
Yep.
and this is also compression.
This is along the same axes.
This is
Against.
exactly. Yeah.
Got it. I was like, that's what I learned. I was like, what did you mean?
Yeah. No. Sorry, I didn't mean to confuse you. But this approximation here, this is an actual approximation. So, I mean, of course, the whole thing is approximation that things are going to respond linearly. Like, in other words, this statement here claims that if you, assuming that you think Young's modulus is a constant for material, which they do, this statement is saying that if you double the stress, you're going to double the length that you're stretched at by or whatever, right? That, of course, is an approximation. That doesn't necessarily have to be true.
It's not perfect, right?
So this whole thing is approximation, but you're going to assume that they're all right because whatever. I'm sure they're right pretty close. This is an actual approximation that you should probably understand why they do it, and therefore this is not obvious. This statement here that the zero equal is not obvious from. It's not a definition, and it's not a read labeling of anything. This is an actual non-obvious. I keep saying that because I mean, like, some things are obvious, meaning if you're confused by them, you should probably start over and be like, okay, what is it? Because it might be a little more obvious. Some things are not, meaning if you think, of course, you should again think about it because it's not quite of course. So that's why I say those words. But I mean, this, if you actually define the angle, you might actually care, because you'd think, I don't really care exactly. I mean, it might be easier to measure this, but you'd think sort of in sort of an abstract point of view, if you think about a bridge and like how much can it like wobble, you might actually want to consider gamma. It just might be a different way to measure it or whatever. You might put, I want gamma to be less than like 1/10 of a degree or whatever, right? Then you would say, well, I can just use trigonometry and then use a Taylor series here. So this is like a Taylor series. So it's plus 4 gamma cubed.
Damn it.
No, it's okay. Just leave it what's in the box.
That's what I'm saying. No, you don't. That just means there's gamma cubed. So if gamma cubed is large, which would only happen for large angles, this approximation is no longer correct.
Oh, yeah, isn't it only valid? I've heard the benchmark is like up to 10 degrees, or is there a different benchmark? The small angle rule approximation.
The small angle approximation is never correct, except at 0. It's always
Right, but-
incorrect.
But like,
As you get higher, it gets more incorrect.
okay,
It actually gets infinitely incorrect at 1 radian, which is like 50 degrees. It gets infinitely incorrect because sine of theta is theta plus 1 or theta cubed plus ... Of course, I'm not writing them, but if theta cubed is bigger than theta, which happens if at 1 radian, you have to use radians here. This is actually an example where you do have to use radians because if you use degrees, the units don't make any sense, like degrees cubed. Radians doesn't have any units. It's just a ratio. Anyway, if theta cubed is greater than theta, like at 1, this becomes bigger and bigger and bigger, and so it gets infinite. So this is not true at all. Because I did a Taylor expansion around 0. Now at theta equals 0, this is identically 0, and that's exactly right. At theta equals anything else, of course, infinitely it is right. But it's not right
You're
like...
never gonna find it.
Yeah, exactly.
Yeah.
But to cut it off after a certain point. Now, if you cut it off after here, it's actually probably pretty good for a while.
It's not converging. You're diverging.
Yeah, you're diverging, right? So they have called a radius of convergence.
Yes.
Now, I wouldn't call that a good approximation, because at 48 degrees, you're not diverging, but you're getting to like not very good
You're
approximations.
not getting close.
Exactly. So what you want to call the benchmark, is sort of arbitrary.
okay,
So sorry, that was like a
that's okay.
terrible answer to your question, but
Deviation. There's a tolerance.
yeah, it's really about taking your output at the final answer, whatever you get, you have some tolerance. What you want to do is propagate that back and see therefore what angle would give me exactly that tolerance, and so it depends on the situation. In general, there's no good rule. I mean, if you say 10 degrees, there are certain situations where 10 degrees would be a horrible approximation, right?
You ever had to spec tolerance for an angle on a drawing?
We kind of do it with our company's template. Like we have a thing in the bottom right.
You never actually do it.
Yeah, that's
You never actually calculate it. So you don't care.
I have not had to do it yet. I'm aware that my company that's above my pay grade. My company takes care of that with the template they told me to use. So I was like, okay.
Oh, I have to do it once. It sucks. It really sucks.
I got one for page 75. There's a graph there discussing the relationship between force and change in length. It's on page 75 of the textbook. I was just wondering if we could discuss it a little bit.
75?
75.
Yeah.
All right. So with
That's this.
all right, so that's Young's modulus at the avenue between force and change in length. So like like how stress is force over area and strain is change in length over length.
Yes.
Right. So Young's modulus resolves this by taking it meets both expressions of force in the middle by discussing force and length. I'm sorry, I'm not wording this very well.
Well,
Basically, so what I should be asking is this line right there. Is it basically that line? What's being graphed is Young's modulus, right? And how it changes depending on how much force there is or how much.
they're holding steady
Okay.
a cross sectional area.
So in this
They're trying
case,
to.
So in this case, the independent variable is change in length,
Mhm.
right? And the change in length determines how much force is being applied to the object in question.
That's
right.
I would say the other way around, but yeah.
But if that's the case, normally the x-axis is resolved for independent variables, right?
Oh, I mean, okay, yeah, you could say it like that. They're just saying, yeah, right. In other words, how much force do I need to apply to change the length by this much? Yeah,
Okay,
sure.
so it's
You're
just-
right.
Okay, but I see your point. So it goes both ways.
I was just trying to say, like, causally, the force causes the change in length. It's not like when you make it longer, it gives you a force. But
All right.
You're right,
more
that's a
force
subtle
applied.
point, yeah.
Okay. So naturally, when it goes backwards, that's compression. When the it's at the bottom left corner.
bottom.
So you see.
Oh,
when it
of the
goes
graph.
up-
Yeah,
graph.
sure.
When it goes up, then it begins
Yeah.
It's not compressed. It's getting pulled. Right?
Yep.
Okay. So going up, it's elastic deformation. When it gets up to yield force, yield is basically like, okay, we're past the breaking point. Now it's just
Yeah.
deformed.
Yes, now it's deformed. This is not true anymore after that point.
Okay.
Because this is a line
And
with a
the-
slope of E, and that's not.
all right.
all
And the
in
yield.
the air.
So the yield force that we have
When
right
you
now is
eventually come to
basically that's also inherent
Well,
to
right, yeah.
testing, right?
But,
Yes.
But now it's
So we can't figure it out with the formula even
No,
for
no.
Young's modulus.
Yeah.
This does not have any information about the yield. Yes.
And ultimate force is just you're gonna break it.
Yeah.
young and young.
Rupture, I guess. Yeah.
So
Plastic, right? It would just mean that like materials tend to behave. I mean, this is all just messy real world stuff. You might call it nice real world stuff, but I would call it messy real world stuff in the fact that this is a nice linear relationship, and unfortunately, in the real world, things like are kind of annoying, and they don't quite do that.
I believe that you're indulging in a redundancy right there. Messy
Yeah.
real world stuff.
But
no,
I want to
I see-
emphasize.
I see
it
your
was for
point.
emphasis.
Okay.
Yeah. So I just mean that it just happens to this graph here is an experimental result.
Okay.
This here is a nice mathematical statement that approximates it at low.
That's,
when it's
low
linear.
applications of okay.
Exactly.
So is it possible then that some materials don't have yield force, like they just have ultimate force? Either it's in one piece or it's broken.
Yeah, I'm sure there are some that never become like maybe a rubber band.
Okay.
A rubber band actually doesn't do this. A rubber band has like it's a complicated. Well, you'll get to it actually. We
Rubber
use
band's
harmonic motion.
Did you what's your background?
Chemical engineering.
Chemical. Okay, so
Yeah.
did you actually ever like do the stress tests?
For
Like
for
we did
for
statics.
prereqs we had for chemistry. Yeah.
Oh, but you never like
Like for
Did the-
chemistry, we did that sort of stuff for like for springs, but we
Oh,
never really
no.
got into the materials themselves or Young's modulus.
oh so you
Like I
never,
knew about that stuff, but I've never really done this.
you never took the piece of steel and pulled it apart.
I can't recall ever being able to pull apart a piece of steel.
No, you did it in what are they called?
The dog bone machines.
The dog bone. Yeah, thank you.
Instron.
Instron.
Ashley can tell. Ashley
will tell you all about it.
because that's their whole business, right?
That's
it's
her
just
entire
measuring
business.
instruments. Yeah.
She's in automation testing.